continuing from where we stopped the other day, check out. An unknown metal reacts with oxygen to form metal oxide having 60% of metal. Calculate equivalent weight of metal. See, what does this mean? That I have a metal, right? Metal may be in a solid state and reacts with an oxygen to form metal oxide, MxOY. Okay. And in the metal oxide, we have 60% of the metal. That means if this is the metal oxide, 60% of the weight is by metal itself. So what you can do, assume 100 grams of metal oxide. Then it implies that originally we had 60 grams of metal, 40 grams of oxygen. That's how we are getting 100 grams of metal oxide, correct? Now, if I know what is the weight of it, I can calculate what is the number of equivalents also. Because by definition, equivalence is weight upon equivalent weight. So 60 divided by equivalent weight of metal, 40 divided by equivalent weight of oxygen, and 100 divided by equivalent weight of metal oxide. Okay, clear? So this can be, and you know that number of equivalents in the chemical reaction will always remain same. Okay. So that is called the law of chemical equivalence. That is, number of equivalents of metal should be same as number of equivalents of O2 should be same as number of equivalents of metal oxide. So this is what you will fundamentally use. So therefore, 60 by equivalent weight of metal is equal to 40 by equivalent weight of oxygen plus 100 by equivalent weight of metal oxide. See, equivalent weight of metal oxide can also be written as equivalent weight of metal plus equivalent weight of oxygen. Got it? And we learned that equivalent weight of oxygen in any form, whether it is O2 or O2 minus or nascent oxygen, correct? In any of these form, we write it clear. The equivalent weight will always be equal to 8. Okay, the equivalent weight is 8. This is a fixed value. Got it? For hydrogen it is 1, for oxygen it is 8, for chlorine it is 35.5. So we will use that here. So 60 by equivalent weight of metal is equal to 40 by 8. So from here equivalent weight is equal to 6 into 8 by 4. So how much? 12. So 12 gram per equivalent. Okay. Just like how we write it per mole, now we write it as equivalent. Everybody clear? So typically whenever you want to calculate the equivalent weight of a metal or equivalent weight of metal oxide or anything like that, this is the basic detailing that you should use always. Finished?
Yeah, sir.
See the next one now. Calculate the oxidation state of iron and calculate fraction of iron in +2 oxidation state in Fe 0.960. Okay. Done. Right. Let's notice this one. See, we have Fe 0.960. These kind of compounds where the ratio is not in a simple numbers is called non-stoichiometric compounds. So that means they are not in a simple stoichiometric ratio. What here we can see is that the overall charge of this compound, that is Fe 0.960, for that it is 0. That's the hint you need to grab. So here I can say 0.96 multiplied by the oxidation state of iron, that plus 1 into -2, which is the oxidation state of oxygen, that total should be equal to 0. Remember, this is how we make the algebraic equation to calculate the unknown uh, oxidation state. So from here we will get x is equal to 2 by 0.96. So this becomes the oxidation state. Okay. So remember, this is the oxidation state now. So 200 by 96. Okay. Clear? This is, to be precise, this is not oxidation state. It is actually oxidation number, because it is an average of the molecules. Because oxidation state is never a simple fraction. Okay. But generally, if the question is given like that, so you should understand that we are talking about that average value. Now, when we have this non-stoichiometric compound, why would this arise? It arises because iron is not present only in one particular oxidation state. It is present in multiple oxidation states. So you can see Fe 0.96 is there, means some part of it must be in the form of Fe plus 2 and some part of it must be in the form of Fe plus 3. Okay. Now you might ask, "Oh, sir, why only these two? Why not Fe plus 4 or why not Fe plus 1? Well, those are oxidation state which are not observed in iron. So yes, this information you must know, that what are the natural oxidation states of the metals. Okay. For iron, got it. And typically you will be asked only these. For iron, nickel, cobalt. Okay. For these, you would usually see, sorry, in manganese also. Okay. Manganese, you will see plus 2, plus 3 more common. Got it? Manganese, in some extent, it will go plus 4 also, but that will be given to you. If it is going plus 4, that will be definitely mentioned to you. Okay. Copper will go for plus 1 and plus 2. So in the questions, if the oxidation state is not given, what are the mixed oxidation states which they can have? This is something which you need to know. Iron, nickel, cobalt, manganese, if it is given, so automatically you take them as having plus 2 or plus 3 oxidation state. In case of copper, take it as plus 1 and plus 2 oxidation state. Okay. Now, when it comes to iron, let us say we have, our question was to find out plus 2, right? So let us calculate this. These are x grams we have, x moles of iron plus 2 we have. Then 0.96 minus x moles will be of Fe plus 3, correct? And now I can write again x moles into plus 2 oxidation state plus 0.96 minus x into plus 3 oxidation state, and that minus 1 into oxygen, which is minus 2 oxidation state. Okay, or let me write down here as minus 2. So plus into minus 2, this overall equal to 0, correct? Now the same algebraic equation, instead of writing oxidation number, I am writing in terms of oxidation states. Got it? Individual oxidation states. So when you do that, what do I get? 2x minus 3x plus 3 times of 0.96, that is equal to 2. So this will be minus x, or x is equal to 3 times of 0.96 and minus 2. This is what you will get. Okay. So if I take 0. Uh, this is 3 into 0.96 minus 2, and that's it. Okay, that is how much we have. So that is coming out to be 0.88. So We got X, that is the number of moles of Fe plus 2 ions. Therefore, percentage amount of Fe plus 2 present in this will be 0.88 divided by 0.96 multiplied by 100. Because originally, how many total number of moles we have? 0.96 moles we have. Okay. So this is coming around 91 percentage. So 91 percentage of the number of moles will be of plus 2, and rest of the moles will be of plus 3. Okay, very standard question, everybody. Please do check once. Right. So everybody, so whenever we talk about titrations, it is a basic technique. It's a technique of identifying, clear, uh, or relating, basically relating concentrations in terms of normality, correct, between two components. But these techniques are only applicable for compounds which reacts extremely fast. Okay, so first term we need to know that valid for kinetically kinetically fast reactions, correct. This is first term you should know. Okay. Next, the second important term is standard solution. What is standard solution? When I use the word standard solution, that means it is a solution whose concentration is accurately known. Okay, solution whose concentration is accurately known. Most of the time, once the concentration is accurately known for a certain compound, we usually store in a round bottom flask. Round bottom flask, like this. Round bottom flask are of different sizes, starting from 1 liter, all the way up to 10 liters. We can have it. Got it? Clear? Next, whenever we make titrations, correct, there are two reagents that we refer to. Okay. Now, one reagent is called titrant, the other one is called titrand. Okay. One second. Is there some kind of a screen obstructing? One second. Oh, sorry, this one. Let me hide this out. I guess now it should not be a problem. Yeah. Right. Check it out. The reagent, okay, with the known concentration, with the known concentration. If the concentration of that compound is already known, okay, we use the word titrant. This is called titrant. Okay. And reagent, reagent uh, that need to be estimated, that need to be estimated in concentration, that is called titrand. This is called titrand. Clear? So what is the procedure in titration? Okay. During titration, we are basically adding, okay, titrant, titrant to titrand. Okay, titrand to titrand. Correct. This procedure of adding titrand to titrand is what we call it as titration. Correct. So in simple terms, suppose if at all I have any setup like this, and here it is been connected to a tube this way. Okay. And from here, this kind of a setup is present wherein we are adding it to a solution here. Okay. So from here, we are trying to add to the solution which is already existing here. Okay. So which one do you think is titrand now? This one is titrand, and the solution which is already present is titrand. Got it? So typically, and titration will have this kind of a setup. Okay. There are mainly two instruments we will use. This instrument which controls the flow of the titrand, that is called burette. It's called burette. Sorry, double R. Burette. Okay. And this one is simply referred as flask or a glass, anything. Got it? So whenever we talk about titration, this is the bare minimum idea you should have. Okay. Correct. So all we are trying to do is this. We are trying to figure out there is two chemicals react to make a completion of a reaction. Titrant and titrand, both of them are two reactants or two reagents which will react with each other and make the reaction complete. So this reaction, when it gets completed, that is called equivalence point. Okay.
So can you repeat this
There
last one?
two reactions are happening. For example, 1 mole of HCl I took 1 mole of NaOH. When both the reactions get completed, that means both the reactants get 1 mole each, and the reaction is been said to be only salt and water, and there is no other reactant left, then we say the reaction is complete. Okay. And that point
That
where the reaction
equivalent.
is
अच्छा, okay. हाँ, ठीक है, got
complete
it.
is called as equivalence point. So this is a theoretical point. The point, okay, at which chemical reaction is complete. Chemical reaction is complete. Okay, which means no reagents left. No reagents left in the flask is called equivalence point. And like I said, it is a theoretical point. Practically, what you will observe, right, where you will stop, that is called end point. Practically, when you observe the same, it is called end point. Okay. Clear? Now, how do we notice that practically where it should be stopping? See, most of the reactions which you perform are both colorless. Titrant is colorless, titrand is colorless. So when you are mixing, let's say you opened the tap of the burette and you started mixing in the flask. So how do we know where to stop? Okay. So what we do, we add a small chemical known as indicator. We add a small chemical called indicator in the flask here, in titrand here. Okay. And indicators are such kind of chemicals which will change the color exactly at equivalence point. Got it? Clear, beta? But since there is no proper control of the flow, that see every ml, every drop might be something close to that of 1 ml or zero point 0.5 ml, correct? So to find out the exact amount of volume becomes difficult. So that's why we will be reaching nearby equivalence point using indicators, correct? And color change that happens due to the indicator, at that color change we will stop the titration and we say, hey, we have reached the equivalence point. May not be exact precise value, but we came to the closest value to the equivalence point. Is the logic clear, everybody? And that is a practical value which you will find it on the burette, that how much amount of volume that you have consumed. Got it? So now the reading of volume, that how much volume of titrant is consumed, that is the volume based on the end point, that is called end point now. So let me write down that the practical point when indicator makes the color change near the neutralization point or near the equivalence point is called end point. In questions, if you are getting the data, that means the data is about end point. Okay. Got it? Now, I hope all of you understood the basic. Uh, it's kind of prerequisite to understand the titration. These are the points you need to learn from titrations. Right? Shall I go ahead, everyone? Right. Now, notice the next point. Correct. The next point is about understanding what are standard solutions. Standard solution. Clear? See, measuring the standard solution, how to make the standard solution, that itself is a small part of theory, but we don't have to worry about that right now. Got it? That how much carefully you have to weight the reagent, how to check out the purity. Okay, then add some suitable solvent, dilute it exactly to the volume what we need. This is a procedure that we need to do, but that procedure is not usually asked in here. You are supposed to write it in a lab manual. Okay, I mean, you have to supposed to write it in your lab notes, correct? And that is something which you need to submit during labs, correct? So that is not a problem here. But what is something which you need to understand is there are two types of standard solutions. One is primary standard, the other one is secondary standard. Primary standard solution. Very important point. Okay. Clear? Now, when do we see something is a primary standard? Primary standard must have these usual conditions. One, relatively higher molar mass. Most of the primary standards have higher molar mass, relatively. Got it? And second thing, they do not absorb moisture. Do not absorb moisture. Okay? In any condition, they do not absorb moisture. Clear? They are non-reactive with light and air. So it's not like they should decompose, you know, in light and air. And second, they should not be neither, they should be efflorescence, efflorescence or deliquescent. Efflorescent is a compound which will lose water, okay, into atmosphere. Got it? And deliquescent means which will absorb moisture from atmosphere. For example, if I take common salt and keep it on a table, what would happen? It will slowly start absorbing moisture. Okay. But on the other hand, if at all I take zinc sulfate, okay, zinc sulfate already has some 7H2O with it. If you keep it on the table, slowly it get dry. That means it will start losing out moisture to the atmosphere. Got it? So that is called efflorescent, and the one which absorb the moisture is called deliquescent. Okay. Neither it should be efflorescent nor it should be deliquescent. Okay. When you have chemicals which are ticking all of these points, then we can convert them into primary standards. Okay. Examples where the primary standards are, where we see them as primary standards mainly are Na2CO3, got it? Na2CO3, K2Cr2O7, clear? Borax, borax, which is Na2B4O7.10H2O, borax. Sodium oxalate, Na2C2O4.2H2O, got it? KiO3, Mohr's salt, okay? Ammonium sulfate dot FeSO4 dot 6H2O. These are the standard, these are some of the primary standards which we'll use more often. Got it? The next one is secondary standards. Secondary standards may not, tick all of these points. Yes, they might have higher molar mass, correct? But they definitely will not tick rest of the parts here. Okay. Higher molar mass, yes. They do not absorb moisture, no. Non-reactive with light or no. Neither efflorescent nor deliquescent, no. So only one factor which is mostly valid is secondary standards is only they might have a better molar mass, but not necessarily rest of the points are ticked. Got it? Okay. Example being, you know, Na2Cr2O7 KMnO4. Got it? H2O2. Okay. And HiO4. Sorry. Na2S2O3. Na2S2O3. Clear? Dot 5H2O. These kind of cases. Clear? They are all secondary standards. Okay. In fact, a lot of solutions are there because majority of compounds they usually decompose in air, they decompose in the presence of light. That's why we can have lots of secondary standards, but primary standard is something which we need to remember properly. And these are some examples. Done, everybody? Now, whenever it comes to titration, let me give you basic idea. No, first, just orally. One is a direct titration. The other one is a back titration. Okay. Here, direct titration means we are taking only two components. One is a titrant, one is a titrant. Correct. The second one is back titration. In back titration, what we have, we will have an excess of reagent. One of them will be excess of reagent. and we add something like a third reagent to complete the titration. Correct. Such titrations are called back titration. So overall, I can say two types of major titrations. Two types of titrations. Correct. So one is direct titrations. Okay. The other one is back titrations. Direct means only titrant and titrant in limited amount. And here back titration means one of the reagent is in excess, and this excess amount will be again titrated with something else. Okay. Now let us understand what are these titrations. There are many titrations. I'm emphasizing mostly on direct titrations. Within direct titrations, we can have redox titrations, acid-base titrations, and so on. So first, let us start with redox titrations. Redox titration is something where we are making reaction between a titrant and titrant, where the overall reaction is a redox reaction. That means when they are reacting, there is an exchange of electrons. Got it? Such type of titrations are called redox titrations. And when it comes to redox titrations, we are supposed to learn two important things. One, whether the titrant, whether the chemical which you're talking about is an oxidizing agent or a reducing agent. Okay. For example, if you have anything as simple as A plus B is giving C plus D here, correct? Then in a redox titration, these two components, A could be undergoing oxidation. Suppose it is undergoing oxidation. If it is undergoing oxidation, you call them as reducing agent. Call it as a reducing agent. And B, it may be undergoing, during the reaction, it is undergoing reduction. It is getting reduced, that means it is called oxidizing agent, right? So these are the 2 points you need to remember, whether they are being used as oxidizing agent or a reducing agent.
Can you go a little of that direct part?
Yeah, clear?
Yes, sir.
Now I'm talking about the compounds which usually act like strong oxidizing agents. Okay, mainly what in our syllabus we have is 4 of them that we need to study: KMNO4, K2Cr2O7, ozone, and peroxide H2O2. This is what we have it for syllabus, everybody. Let me repeat. We have strong oxidizing agents. Out of all the strong oxidizing agents, the oxidizing agents which we will learn are KMNO4, K2Cr2O7, peroxide form H2O2, and ozone. Okay, let's start with KMNO4. Okay, see, KMNO4 by nature it is purple pink color. Okay, it's crystal. It exists in a crystalline form, and those crystals are purple pink in color. Okay, now KMNO4 makes the reactions in acidic medium as well as basic medium. The KMNO4 When it makes a reaction in acidic medium, this is what happens. In acidic medium, it will convert into Mn plus 2. In a basic medium, this basic medium should be about very dilute. In a very dilute solution, very dilute basic solution, it will gain 3 electrons and convert itself into MnO2 plus some colorless solution. Got it? Now, since the number of electrons are known, from here I can calculate what is equivalent weight. Equivalent weight will be equal to molecular weight by 5 for KMnO4 in acidic medium and molecular weight by 3 in basic medium. Similarly, when it comes to K2Cr2O7, K2Cr2O7 is an orange-red crystals. And this orange-red crystals in acidic medium will convert into green color solution. It will convert into green color solution. And here it will be molecular weight by 6 because it will be gaining 6 electrons in here. Okay. While in basic medium there is only color change, it is a non-redox. It is a non-redox reaction. So you can see from orange red it will convert into yellow, but it is not a I mean it is a non-redox reaction. There is no redox reaction happening in here. Okay. So equivalent weight in this case will be simply m by 2. Why? Since it is a non-redox reaction, you will only check out them as a salt. And what is the definition of molecular weight? Equivalent weight in terms of salt, beta? In terms of salt, total positive charge or total negative charge, correct? So it is supposed to be 2K plus and Cr2O7 2 minus. So total, how much negative or positive charge it is holding? 2. So that means it will be molecular weight by 2. Understood? Right. Okay. So let me write the equations, what you need to exactly know. See, this is the equations that you need to know. Chemical equations. First one is manganese, correct? MnO4 minus, correct? MnO4 minus plus 5 electrons plus 8H plus, that is converting into Mn2 plus 4H2O. Okay. The reduction potential for this value is 1.51 volts. This is called reduction potential. Okay. Next, when it comes to MnO4 in basic medium, it is 3 electrons. Got it? So it is about 3 electrons which it is consuming plus 2 moles of H2O liquid. It is converting into MnO2 as a precipitate, clear, and releasing 4OH minus. E naught, the reduction potential for this is 1.65 volts. Got it? 1.65 volts. And K2Cr2O7 plus 6 electrons plus 14H plus. This will convert into 2 moles of Cr plus 3 plus 7H2O. Okay. This will be with potassium dichromate. Clear? The E naught value of potassium dichromate is 1.33 volts. Got it. Now, as of now, since we haven't discussed much terms about electrochemistry, you remember it this way. Whosoever has more E naught value being positive value, more the positive value, which means it has more power to get reduced. Got it? Now, out of these 3 reactions which I gave you, half reactions, which half reaction do you think suggests that it is a powerful reducing agent? You can see this one, right? So MnO4, theoretically, MnO4 out of these 3 reactions, MnO4 is a stronger oxidizing agent compared to MnO4 in acidic medium and K2Cr2O7. Clear
सर तो
everybody?
अगर हम पॉजिटिव वोल्ट्स बढ़ाएंगे तो मोर रिड्यूसिंग पावर होगा या ऑक्सीडाइजिंग पावर? ऑक्सीडाइजिंग पावर ना?
ऑक्सीडाइजिंग पावर, ऑक्सीडाइजिंग
हाँ
पावर।
वही वही। हाँ बस ठीक है।
ठीक है, कि दूसरों को ऑक्सीडाइज करने में वो बहुत ज्यादा स्ट्रांग है। ओके, खुद रिड्यूस हो
और
जाएगा।
अपने आप रिड्यूस ज्यादा होगा, ठीक है सर।
यस। क्लियर एवरीवन? राइट। Now, these are standard reactions of KMnO4 in acidic medium. We must be able to assess that what could be the products given. Usually, when these reactants are given, you are expected to know the products directly. In the questions, you will not be given that what is the product and you know based on the product suggest something. No, this is something which you have to know that KMnO4 is reacting, K2Cr2O7 reacting. Then what is the product that it can form? Okay, so starting with check out when it comes to I minus. Okay, in the case of I minus, what does it give? I minus, you will get I2 plus Mn plus 2. With Cl minus, it will become Cl2 plus Mn plus 2. Here, NO2 will become NO3 minus and Mn plus 2. This will become arsenate plus Mn plus 2. Arsenite will become arsenate. Sulfite will become sulfate. SO4 2 minus plus Mn plus 2. If you have peroxide, it will become O2 plus Mn plus 2. Oxalate will become CO2 plus Mn plus 2. Fe plus 2 will become Fe plus 3 plus Mn plus 2. Tin will also become Sn plus 2, plus 4 plus Mn plus 2. And zinc will become Zn2 plus Mn2 plus. Okay. H2S will become colloidal sulfur and Mn plus 2. Any form of S2 minus will become colloidal sulfur and this one. Okay. Clear?
सर आपने H2O2 के लिए लिखा है O2, इज दैट पेरोक्साइड और जस्ट O2?
This is normal O2. From peroxide, it is
हाँ ठीक है।
converting into O2. Okay.
ठीक है।
Now, good part about this, whatever we are studying right now, good part is this is amalgamation of almost 4 topics: electrochemistry, T block elements, redox reactions, as well as ionic equilibrium. So you can imagine in all these 4 topics, you will come across these same things. Okay. So learn it as many times as possible. This is the most important area. Okay. Next, as much as basic medium reactions are concerned, KMnO4, what are the basic medium reactions? Well, there are many, but these three are the ones which are there for your course. So remember that when you react KMnO4 in basic medium, I minus will convert into IO3 minus. Okay. This has been asked in JEE mains recently almost 2-3 times. Okay, 2025 there was questions based on that. 24 also, JEE 24 also there are questions based on this. Okay, so I suggest remember clearly that I minus converts into IO3 minus. And what happens to manganese? It will become MnO2 precipitate, a black brown precipitate. Oxalate will become CO3 2 minus and MnO2. Okay, thiosulfate will become SO4 2 minus completely, and manganese will become MnO2. Okay, these three are the main reactions that you need to remember in basic medium. Got it? Done, everybody? Now, before going into K2Cr2O7, I want you to emphasize on this point. If at all I have reduction potential of chlorine taken Cl2 plus 2 electrons is converting into 2 Cl minus. The reduction potential value of chlorine is 1.36 volts, which means given the chance K2Cr2O7 is reacting with Cl minus, right? Do you think this reaction will be possible? That is Cr2O7 2 minus plus 2 Cl minus, that it will convert into Cl2 and 2 Cr plus 3. Is this reaction possible? Answer is no. Why? Because as per the given values, it appears like chlorine is a better oxidizing agent than K2Cr2O7. Correct? So do you think K2Cr2O7 will have enough strength to oxidize chloride ions? No. Clear, everyone? You notice that they are very, very close values. Okay, but yet who is dominant here? Chlorine is a dominant factor. So oxidizing power wise, chlorine is better than K2Cr2O7. But on the other hand, compare that same thing with MnO4 minus. Now, when it comes to MnO4 minus, is this possible that MnO4 minus plus 2 Cl minus trying to convert into Cl2 plus Mn2 plus in acidic medium? Is this possible? Absolutely. Why? Because you can see the value of KMnO4 here is 1.51 while chlorine here is 1.36. So who is a better reducing agent? MnO4 minus. Is this logic clear, everyone? Okay. See, whatever I'm explaining, this is all a part of D block elements as well. You will be studying, you'll be learning all these same necessary terms, whatever the justifications we are giving. This is all something we'll learn again in D block, but please start revising from now itself. So one thing we learned that KMnO4 is relatively stronger oxidizing agent than chlorine, and then comes K2Cr2O7. Okay. So now see the reactions of K2Cr2O7. In the case of K2Cr2O7, pretty much the reactions what happens with KMnO4 are exactly same here also. So the products are very much same. Let me write I2 plus Cr plus 3, NO3 minus plus Cr plus 3, ASO4 3 minus plus Cr plus 3, SO4 2 minus plus Cr plus 3. Okay. And oxalate, when it comes to oxalate, CO2 plus Cr plus 3, iron plus 2 plus Cr plus 3, and tin, Sn plus 2, sorry, plus 4 plus Cr plus 3, zinc plus 2 plus Cr plus 3, and colloidal sulfur and Cr plus 3. So these reactions are exactly same in all these cases. Where the difference comes is, obviously it cannot oxidize Cl minus, but what you would notice is it will form a compound which is non-redox compound. This is a non-redox compound which is CrO2Cl2. Okay, this is red color vapors. Okay, known as chromyl chloride. Chromyl chloride. Chromyl chloride has huge significance in inorganic reactions. We will be learning a lot about that going ahead. But as of now, if the compound is given anywhere, chromyl chloride wording is used. You should know what does that mean. So it is CrO2Cl2. Okay. I hope you understood the obvious reason why it is not able to oxidize Cl minus. Instead of oxidation, it went into a non-redox reaction. Okay. Same happens with
The two
peroxide
minutes,
also.
just writing.
Ishman, could you repeat?
Yeah, I'm just writing. So 1 minute.
I'll show you once again. 1 minute. Let me finish this. When it comes to peroxide, same logic. Peroxide is also a stronger oxidizing agent in acidic medium. It will convert into a blue color solution, which is because of the formation of CrO5. CrO5 is a butterfly type of structure, which we have learned it earlier. This is how it appears. This is blue in color. Okay, tetraperoxy chromium oxide. So here we have four tetraperoxides. So it is tetraperoxy chromium oxide. That is a compound. So you notice that peroxide and chlorine, both of them are relatively stronger oxidizing agents than K2Cr2O7. Okay, now you guys can make a note. The KMnO4 in acidic medium, M by 5. KMnO4 in basic medium. When you are using the word basic medium, we are referring to this one, OH minus in concentrated form. What is it changing to? From plus 7, it is changing to plus 6. So which means it is consuming 1 electron. So the valency factor should be 1. So the equivalent weight of MnO4 minus must be equal to molar mass by 1. This should be the equivalent weight. But if I ask you what is the equivalent weight of KMnO4 in neutral medium, it is M by 3. What is in acidic medium? M by 5. So M by 5, M by 3 and M by 1. Okay, these are the values. Okay, clear? K2Cr2O7 anyway does not have a redox reaction in basic medium or neither in aqueous solution. K2Cr2O7 is only asked for one reaction, that is how it behaves in acidic medium. Okay,
तो वो जो आपने लिखाया M/5 that is for KMnO4 ना
in acidic medium,
वन
KMnO4 in acidic medium, KMnO4 in
हाँ
basic
ठीक है
medium is M by 3. Sorry, neutral medium is M by 3. Basic medium is M by 1.
ठीक
Okay. Hmm. Done? Right. Now let's talk about the ozone reactions. Okay. Ozone is also one of the, strongest oxidizing agent. Clear? And what is the type of reaction does it do? Okay. Ozone is blue color in solid or liquid phase. Got it? And its valency factor, whether it is taken in acidic medium or basic medium, usually be always 2. Okay, what does it do? See, O3, okay, will always give you O2 plus nascent oxygen. It will give you O2 plus nascent oxygen. And it is this nascent oxygen which will consume the 2 electrons to convert into O2. Got it? Sorry, to convert into O2 minus. To convert into O2 minus. So wherever there is an ozone, right? If you are using it as an oxidizing agent, this is the reaction you are expecting. That is O3 will consume 2 electrons, will convert into O2 plus O2 minus. This is what you expect. Now the same thing O2 minus, because here we have O2 minus here, O2 minus, that is been kept in acidic medium. Suppose if it is there in acidic medium, correct? If it is in acidic medium, it will convert itself into H2O. Okay. And if it is given in basic medium, it will convert itself into OH minus. Okay. So that means it will remain as OH minus. That's it. Got it? So remember how the ozone behaves in acidic medium, how the ozone behaves in basic medium. Okay. So overall, if I write ozone in acidic medium, what does that mean? See, this is what it meant. O3 plus 2 electrons plus H plus is converting itself into O3, sorry, O2, O2 plus H2O liquid. So which means I should have 2H plus here. Done. This is in acidic medium. In basic medium, it will again take 2 electrons plus O2 minus converting into, sorry, O2 minus plus H2O, correct? That will be taking up and converting itself into O2 plus 2OH minus. Okay, got it. So this is how it will be appearing.
तो थोड़ा ऊपर जाओ.
But honestly, what you need to learn from here is that ozone, whether it is in acidic medium or basic medium, its valency factor is always 2. That's what is important from this topic. Because here the questions are mostly about the valency factor. Next. Next term is about peroxide, H2O2. H2O2 also acts like both oxidizing agent as well as reducing agent. Okay, so let me show you that. Acts as both oxidizing agent as well as reducing agent. Okay, when it is used as an oxidizing agent, what do we expect? That H2O2, right? H2O2 will consume two electrons and converts itself into H2O plus O2 minus. Just like in ozone, here also it will convert into this form. And as a reducing agent, what do we expect? That H2O2 will convert itself into O2 plus 2H plus 2 electrons. So that means it is giving away 2 electrons. So again, what did we learn? The valency factor for peroxide, both as an oxidizing agent or as a reducing agent, will always remain 2. So it will always involve into 2 electrons for accepting or for giving away. In both cases, it will give you these 2 electrons. Done? Right. More about details of peroxide, you will have a separate topic for this. You have a separate chapter only, hydrogen chapter, in which you will study everything about peroxide. As of now, you will notice one thing, that the oxidizing nature of peroxide in acidic medium is greater than K2Cr2O7 in acidic medium. This is the point that you need to remember. So peroxide will have a stronger oxidizing ability than K2Cr2O7. Okay, right. Clear? Next, coming to iodine. Okay, iodine is a mild oxidizing agent. Okay, it is not used as an oxidizing agent everywhere. Yes, it is a mild oxidizing agent, specifically when you're reacting that with a compound called hypo. Okay, so here it is about reaction with hypo. Reaction with hypo. Now, what is hypo? Hypo is a chemical name given for NaS2O3 dot 5H2O. Okay, sorry, industrial name given for this one. What is the chemical name? Sodium thiosulfate. This is sodium thiosulfate. So sodium thiosulfate, when you react with I2 plus Na2, S2O3 in aqueous. That means you added sufficient water into it, correct? In that case, it will convert into 2NaI, okay, plus Na, Na2, Na2S4O6. This is called sodium thionate, tetrathionate, tetrathionate. Okay. Here, iodine, 1 mole of iodine gas or iodine molecule is converting into I minus. Clear? So here we can see iodine gas has been added to this, and this is how the reaction has been done. And the valency factor in this case will be 2. Valency factor is 2. And what is the valency factor for sodium thiosulfate? It is 1. Why? See, for 1 sulfur, if you notice, the oxidation state is plus 2. Sorry, for 2 sulfurs, it is, if you notice oxidation state, here for 2 sulfurs, you are getting it as plus 2. Okay. And same way for 2 sulfurs, if you notice, you are getting oxidation state as 2.5. Okay. I mean, sorry, for 1 sulfur, 1 sulfur 2 and 1 sulfur 2.5. So if I take it for 2 sulfurs, it will be 4 and here it will be 5. So how much is the electron difference? 1. 1 electron has been transferred for every 2 sulfurs here. Done? Everybody, please check it out. If you have any doubt, let me know. Right. Now, next notice. These are typical oxidizing agents which we'll be using. In fact, in the reactions, we'll come across uh, these reagents only. The next part is understanding, you know, reagents, reagents as oxidants, which means oxidizing agents, reductants, reductants, or both. Got it? If you have to figure out whether the the reagent is oxidant, reductant, or both, then how do we notice? See, simple. Usually, if we have a group 13 elements, for example, if we have boron, so boron, aluminium, you know, uh, gallium, indium, thallium. Okay. Typically, their borderline oxidation states, the +3 oxidation state, +1 oxidation state, and 0. These are the most common ones which you will notice. Got it? These are the common oxidation state which you will notice. So even if you take boron can convert into +3. It can convert maybe to +1, but very rare. But otherwise, it will exhibit in 0. So suppose if you have a boron, only boron given, can I say the boron will act like a oxidizing agent as well as reducing agent? Think about it. If I give you boron, can I say boron with a 0 oxidation state? Just pure boron I took. You know that this boron can convert into B+3. But can it convert into something like B -3 or -2 or -1? No. Because group 13 elements does not have that much electronegativity that they can accept some group elements or some other elements to convert itself into having minus oxidation state. Therefore, if boron is at 0 oxidation state, what can I say? That means I can say it can only act like reducing agent. That means it can get oxidized, but it cannot get reduced. Is that clear? So what I can say is that boron in this case is only reductant. It only reductant. That means it's a reducing agent. It cannot act like a oxidizing agent. Similarly, if at all I have some compound where the boron is plus 3 oxidation state, you know that plus 3 oxidation state can only go up to boron 0. So in that case, B plus 3 is only oxidant and it cannot be reductant as well as oxidant. Clear? I guess this idea is clear, everybody. Right. So if you just know the boundaries of these elements, you will be able to figure out, correct? If you know the boundaries that yes, this is where it will go, you know, whether it will go towards positive side or a negative side. If you know that, that is more than sufficient. So check it out. Group 14. In group 14, carbon can exhibit anywhere between -4 to +4, while silicon, germanium, tin, and lead, they exhibit anything from 0 to +4. Okay. Group 15, nitrogen and phosphorus can exhibit anywhere from -3 to +5, while arsenic, antimony, bismuth, they are restricted between 0 to +5. Group 16, oxygen, sulfur, selenium, they all go anywhere from -2 to +6. Of course, uh, oxygen I'll write it separately because oxygen does not get +6. Okay, so oxygen -2 to +2, while sulfur, selenium is -2 to +6, and tellurium, polonium is from minus uh, sorry 0 0 to +6. Lastly, group 17. Group 17, they exhibit anywhere from -1, all of them. So fluorine, chlorine, bromine, iodine, they can exhibit anywhere from -1 to +7. Of course, fluorine does not show all of them. Fluorine only shows -1. So here fluorine will only show -1 and 0. Okay, clear? These are the boundaries you should know for every group. And similarly, when it comes to manganese, okay, manganese in any form can be between 0 to +7, and chromium can be from 0 to +6. Iron can be from 0 to +6. Of course, the +6 ones are very rare, but yes, there is a chance of iron also showing +6. Okay. Clear, everyone? Is a very important thing to learn. This is a part which is there for JEE mains from P block.
तो ये
Okay.
आपने above F आपने क्या लिखा एक बार समझा सकते हो?
Above,
वो जो आपने बोरॉन का लिखा है वो एक बार समझा सकते हो वापस?
see, boron exhibit करता है somewhere between 0 to 3 only.
हम्म.
हो सकता है उसके पास +1 हो, +2 हो, +1.5
हाँ,
हो,
दैट पार्ट आई
+2.5
हाँ.
हो, anything. But it would be between 0, 3, including 0 and 3. Okay. Now there is I took pure boron in some chemical reaction. Now tell me, what are the chances of boron to convert into +3 side and -3 side? -3 तो exhibit ही नहीं करता है, तो ये डायरेक्शन में तो जाएगा नहीं. तो boron can only go towards +3. Agreed?
या कर.
Since it is ability is only to go in one direction, which means what is this direction? It is a direction where it can get oxidized,
या.
which means it can be only used as reductant. It cannot be used as both.
हम्म. फिर वो
Okay.
राइट पे क्या लिखा है?
Same way, there is a compound like, boron having +3 oxidation state. Let's say sodium
हम्म
borate, Na3BO3. Here oxidation state of boron is +3. ये कंपाउंड लिया मैंने. अब ये
हम्म
कंपाउंड को किसी के साथ रिएक्ट करो, आप एक्सपेक्ट क्या कर सकते हो इफ इट इज पार्टिसिपेटिंग इन रिडॉक्स? दैट बोरॉन कैन ओनली गेट reduced.
हम्म
करेक्ट, इट कैन नॉट गेट ऑक्सीडाइज ना बेटा. दैट इज मैक्सिमम ऑक्सीडेशन पे ऑलरेडी रीच कर चुका है.
हम्म
बोरॉन का मैक्सिमम ऑक्सीडेशन स्टेट है +3 और वो
या
रीच कर
गॉट
चुका
इट
है.
सर,
ओके.
गॉट इट।
Everyone clear with these cases? Now here we'll write three terms. R means only reductant. O means only oxidant. Okay. RO means both. Correct. Now these are the examples which I gave you. You need to figure out whether they are R, O or RO. Everyone understood what to do? So take a minute's time and check. First, what is the oxidation state on carbon? -4. So which means it can only act like reductant. Here +4. That means it can only act like oxidant. +2, which means it can act like both. Carbonate +4. So it is only oxidant. C3O2. How much you are getting? 3 carbons. Just check out oxidation number, okay? Average oxidation number. How much it is? 4 by 3. Correct? So it is 4 by 3. So obviously it can act like both. SO2 +4. Sulfur can go up to 6. It can go to -2 also. That means it can act like both. Here it is +6. Sulfur here is +6. If it is +6 means it can act as only oxidizing agent. Sulfur -2. So only reductant. Chlorine -1, which means only reductant. H3PO5. Phosphorus is +5. So only oxidant. HNO3 +5. Only oxidant. N2O4, here it is -4. Sorry, -2. For one nitrogen, it is -2. So since it is -2, that means it can do both. So RO, correct? Chlorine +4, so RO. Phosphorus +3, so RO. Here +5, so only oxidant. Here it is +4, so +4 means both RO. +5 means only oxidant. +4 means only oxidant. +2 means RO, both. CrO5 +6 means only oxidant. Iron is 0. Here can you see it is 0 oxidation state because carbon monoxide is 0. So it is 0 oxidation state. 0 oxidation state means it will be giving uh, only reduction. Okay. That means it can only undergo oxidation and act like reductant. Iron here is +2. +2 means RO. It can be reduced also. It can get oxidized also.
So could you repeat how we decide whether something can be RO?
It should be somewhere in between their boundaries.
अच्छा, okay.
Okay. Any doubt? Everybody? Right. So now let's see. Before going into further detailing about peroxide and oleum and everything. Okay. First, let us do few questions, correct? And then we can go ahead with those terms. Check. Here, before starting the question, you need to understand, especially compounds when they are used in acid-base reaction or when they are used in uh, redox reaction. So, redox versus non-redox. Redox versus non-redox cases. Okay. For example, if at all I have H2C2O4, H2C2O4. Now, when I'm treating this with NaOH, NaOH, clear? Then what does it convert into? The product is Na2C2O4 plus H2O because it is an acid-base reaction. So it is non-redox. And when you are reacting something like KMnO4 with H plus, then what will it do? It will convert itself into carbon dioxide, correct? Plus Mn plus 2. So here it is a redox reaction. See how the definition is. What is the valency factor in this case? Here valency factor is how many number of H plus ions it can give. So 2. It is number of ionizable H plus ions. And here valency factor when you calculate, what is it? How many electrons are being transferred? Oxidation state of 2 carbons is plus 6. And oxidation state of 2 carbons in here is plus 8. So here again the valency factor is 2, but here it is number of electrons transferred. So be aware of the basic definition. So in one case it is about how many H plus ions it is giving. The other case it is about how much electrons it is transferring. Okay. Now tell me if the same case is being utilized this way. NaH C2O4 dot H2C2O4. If this is a compound I took, and once I'm reacting with NaOH, and once I'm reacting with K2Cr2O7 as an oxidizing agent. Okay. In this case, it will become only Na2C2O4. And this case, it will become carbon dioxide. Now tell me what is the valency factor here and what is the valency factor here. Check out in this case, when it is becoming acid-base reaction, because NaOH, when you react with this compound, it is an acid-base reaction. In an acid-base reaction, how many ionizable H plus we have? These are 2 hydrogens, this is 1 hydrogen. So there are 3 ionizable H plus ions. While in the second case, when you're treating with K2Cr2O7, this 2 carbons and these 2 carbons, total 4 carbons are there. Everything is getting oxidized. So I will get, total 4 moles of carbon dioxide. And total how much is the charge? Because each carbon has plus 3 oxidation state. So total charge of carbon is plus 12 here. Here it is plus 12. And here each carbon has plus 4. So it is plus 16. So how many electrons are transferred? 4. So this time the valency factor will be 4. When it is acid-base reaction, it is 3. When it is redox reaction, it is 4. Okay. I guess this part is clear, everybody. Right. Similarly, if I give you one more case like that, I have Na2C2O4 dot KHC2O4 dot H2C2O4. This is a salt I have given, and I want you to treat that with NaOH once and K2Cr2O7 in acidic medium once. So this will convert into Na2C2O4 because here you will assume only acid base reaction, and here you will make an Redox reaction. So in a redox reaction, how many? 6 moles of CO2 will be formed here. So what is the valency factor in both of them? So in the first case, it is clear the valency factor is 3. Second case, now the valency factor is 6. I hope all of you understood this point. Please make a note of it. See, check. What is strength of peroxide? H2O2 usually decomposes on its own to give H2O liquid plus half O2. But here it should be added to water. So that means whenever the pure solute peroxide is added to water, this is a reaction you can expect. Okay. Now, volume strength is measure of how much amount of peroxide is present in aqueous solution. Okay, volume strength is one way of measuring that what is the purity of peroxide which is present in the aqueous solution. How do we do that? Basically, by definition, volume strength is how much amount of volume that is collected at STP at a molar m molar concentration of H2O2. Okay, so in simple terms, correct. So if you want to if you decode that in simple terms, what does this mean? Check. If you have peroxide H2O2 in aqueous solution and it is converting into H2O liquid plus half O2 gas. Okay. Now notice what we can write. Imagine I take 1 mole of peroxide here, 1 mole. Then how much moles of O2 is expected to come out of it if all 1 mole is getting consumed? So imagine if all the 1 mole is getting decomposed. So I should get half a mole of O2, isn't it? Half a mole of O2. So now imagine if this 1 mole is present in 1 liter. Okay. In 1 liter. In 1 liter it was present. Then what will be the number of moles here? I mean, molarity is here is 1. Molarity is equal to 1 divided by 1. So which is 1 molar. Correct? So what I'm assuming that for 1 molar peroxide solution, I'm expecting to get half molar O2. Okay, I'm expecting to get half molar O2. Then if you have number of moles of H2O2, now I'm replacing that as capital M moles. Then volume of the solution, I'm taking it as 1 liter. Okay. Then molarity in this case will be equal to number of moles of H2O2 divided by 1 liter, which is M, because M by 1 is M. Here the molarity M is equal to this much. Now tell me about this one. If for 1 mole, half a mole is being released, for M moles, how much should be released? Okay. So number of moles of O2 that is released should be equal to M by 2. This many moles should be released. M being the molarity also. Okay. Correct. So in that case, can I say that if O2 is collected, O2 is collected at STP, if it is collected at STP, then we can say volume of O2, O2 for half a mole, for 0.5 moles will be equal to how much? 11.2 liters if it is, NTP, and 11.35 liters if it is STP. Correct. NTP means 1 mole is 22.4 liters. STP means 1 mole is 22.7 liters. Correct. And therefore, now if these are the number of moles, then I can say for M by 2 moles of O2, the volume occupied by oxygen will be equal to how much? M by 2, because for 1 mole it is occupying half. So for this M by 2 moles means you just have to multiply that M by 2. M by 2 times of sorry, M by 2 moles only, right? So that means M by 2 multiplied by how much we have? 22.4 liters if it is NTP, and M by 2 into 22.7 liters if it is STP. Okay. So from here we will write Vs. Vs means volume strength. So volume strength Vs by definition has become molarity into 11.2 liters at NTP and molarity into 11.35 liters at STP. Okay. So this is the formula you need to remember. So Vs, either you write it this way or small s, that is equal to M into 11.2 or 11.35 depending upon what you are using. Clear? This is the formula that is to be derived. So whatever be the given term is, sometimes molarity is given, calculate volume strength. Volume strength is given, calculate molarity. Okay. Now sometimes strength is mentioned in gram per ml or gram per liter. Okay. If strength of peroxide is given in gram per ml or gram per liter, in that case, how do we figure out? See, molarity is equal to number of moles of O2 into 1000 divided by volume of solution in liters, sorry, in ml. This is a basic definition, molarity's definition. And number of moles can be written as weight of H2O2 divided by molar mass of H2O2. So molar mass of H2O2 multiplied by volume of solution in ml. And that can be written as weight of H2O2 into 1000 divided by 34 times of volume of the solution in ml. Okay, clear? So from here, can I say that weight of H2O2, by the way, this we have already figured out as volume strength divided by 11.2, let's say. This is what we discussed. So from here, can I write weight of H2O2 divided by volume of solution in ml. So what are we getting? This is the strength now. So expressing strength in gram per ml. So that would be equal to volume strength into 34 divided by 1000 into 11.2. So remember how the question is asked. If the question is asked to find out the strength in gram per ml, this is the formula you will use. If it is gram per liter means just this 1000 will not be there. That's it. Everyone, please check. Part is clear. Right. Let's quickly go through these questions now. Find molarity, volume strength when 17 gram of peroxide pure is added to H2O and made it into 100 ml of solution. It is made it into 100 ml of solution. So first, based on the information, we can easily calculate what is the molarity. Okay, so we'll start with that first. Molarity is equal to, number of moles of H2O2 divided by volume of solution in liters. This is the basic definition. So number of moles includes 17 by 34. 34 is the molar mass. N2 volume is 0.1 liters because it is 100 ml, so it is 0.1 liters. So therefore, this is coming out to be 5 molar. Correct. So it is a 5 molar solution. So for that, what will be the volume strength? Volume strength will be equal to 11.35 into 5 molar. Okay, if you are calculating at STP, and 11.2 liters into 5 if you are calculating it as NTP. Correct. Next, strength. See, in this question, it is clearly mentioned. What is the strength? Strength is asked in gram per ml. So if it is gram per ml, this is the formula which we derived. So volume strength into 34 divided by 1000 times of, okay, 11.2 or 11.35 depending upon what is the standard that is given. So that standard will be equal to volume strength is 11.2 into 5 into 34 divided by 1000 into 11.2. So that 11.2 will get cancelled. So you'll get this as you know, 0.17. This will be the strength. Okay. I suppose everybody got that. What is volume strength? Yeah. See the next question. 1.7 percentage weight by weight of peroxide is present with density of 1.2 gram per ml. Find the volume strength of peroxide. We need to find what is the volume strength of peroxide. Now, percentage weight by weight, we know how to relate it. Density and percentage weight by weight, we know how to relate it. That is, molarity is equal to percentage weight by weight into density of solution into 10 divided by molecular weight of solute. Okay. This I would usually remember it like a formula. That makes it more easier, especially for when you have percentage weight by weight. So percentage weight by weight is 1.7, density is 1.2 into 10 divided by molecular weight. Molecular weight of peroxide is 34. Correct? Done? Right. So this value is coming out to be 0.6. So volume strength is coming out to be molarity into 11.35. So that is equal to 0.6 into 11.35 in liters at STP. So I want all of you to please do check these questions. Very simple ones. Peroxide questions are mostly clubbed with the redox titrations. Okay. So there we'll discuss it more. Right, Shauri, that is correct. Done. This is important topic. What is percentage oleum labeling? How do we label oleum? Okay. Now, what exactly this means? See, in the chemical industry of manufacturing H2SO4, that is our object is to extract prepare H2SO4. See, the main reaction that happens to calculate H2SO4 is this one. We take the vapors of SO3 and let it pass through a moisture, that is H2O, to convert into H2SO4, you know liquid which is in a pure form. Correct? This method is called contact process. Contact process. Industrially, this is how peroxide H2SO4 is being prepared. But there is one problem with H2SO4 here. Such a pure form of H2SO4 is highly fuming. Highly fuming. Fuming means it will keep on bubbling up. So maintaining this H2SO4 in the pure form is very difficult. It will keep on bubbling out again, giving away SO3. So controlling this H2SO4 becomes a challenge. So if we can't control that, and if let's say from one place, okay, imagine I have my own plant of H2SO4 and I got one order. Let's say some industries have made an order. Clear? They will ask me to send some 32 metric tons of H2SO4. Clear? And imagine from Hyderabad I have to send all the way to Mumbai. Got it? That's the transportation which I have to do. So obviously I can't send H2SO4 in a pure form because that is highly fuming, highly corrosive with metals, highly reactive with non-metals. So somehow I need to stabilize that H2SO4. Got it? So what will I do? I will take H2SO4, the fuming H2SO4 which I have prepared, and immediately add some excess amount of SO3 gas. Okay. Now this SO3 gas, the minute it goes in, excess amount of gas goes into the H2SO4, it will become a stable, thick solution now. That is H2S2O7. Now this is stable, thick solution. Okay, clear? Almost like a semi-solid it will become. And this compound is what we call it as oleum. Clear? So now I will, instead of preparing H2SO4, what will I do? I will actually prepare oleum. Okay, but I need to mention now I add this oleum to various barrels. Okay, let's say 10 barrels I have added like this. This is a 10 barrel which I have to transport. Okay, so this is the oleum which has been written. But how would somebody who's working in some industries know that what is the percentage amount of H2SO4 present in it? Correct, isn't it? So what will Samyak do? You will hire some a chemist, isn't it? So they can decode that. So that is where here on these barrels it will be written something like this 109 percentage. This is the hint or a code. Got it? So if it is written 109 percentage, 108 percentage, 105 percentage, 112 percentage, 102 percentage, this type of labeling is been done. Okay, so that's what we are trying to understand. What is this labeling means? This is what we call it as percentage oleum labeling. All right. Now let us understand how do we supposed to give this labeling. Because only when the labeling is been done, after the transport is been done, then they know how to convert excess amount of SO3 also into H2SO4. So what is happening here? Imagine I took 100 grams of oleum. So this is the research wing. You know, on the other end, on the industry, there is a research wing where they took this 100 grams of oleum. In that 100 grams of oleum, what is the quantity that is present? There are only two components present. One is H2SO4, the other one is SO3. Let us assume the amount of SO3 is X grams. Then how much should be H2SO4? It should be 100 minus X grams. Correct? It should be 100 minus X grams. Now, I am supposed to add some amount of water to oleum so that whatever the excess amount of SO3 is present, that will also convert into H2SO4. Isn't it? That is what we are supposed to do. So which means, suppose if at all I have x grams here, correct? By stoichiometric ratio, one thing is for sure, that ideally for every 80 grams, I require 18 grams to convert into 98 grams of H2SO4. But now imagine if at all I have only x grams. If you have x grams, how much amount of H2O should be added? Right? So the weight of H2Os that need to be added is 18 by 80 times of x. This many grams of water should be added. Correct. So what is the labeling? How would I label that? Now see how the labeling is been done. Labeling is done like this: 100 plus weight of water that you need to add so that everything will become H2SO4. So that is 100 plus 18 by 80 into x. This much is the labeling that you will do. Clear, everybody? Now let us do the reverse one. Suppose if it is given 109 percentage oleum is given as a label. अब इसको आपको decode करना है. So what do? We write simply 109 is equal to 100 plus 18 by 80 into x. So that is 9 is equal to 18 by 80 into x. Okay. So that goes x is equal to 40. So, sorry, 40 grams. So which means for every 100 grams of oleum, H2S2O7, for this much oleum, what I did, I have 60 grams of H2SO4 plus 40 grams of SO3. Originally, this is how much in the industry, when we manufacture, this is how much we have added. Clear, everybody? Please do check and let me know if you have any problem. Check. First example is make the labeling of this one. Second example is if I have 1 gram of SO3 added to 5 grams of H2SO4, then you have to label it again. Got it? Do that. First one. First one is easy. So you need to just simply check out how much amount of water that you need to add. So which is 18 by 80 multiplied by weight of SO3. So 18 by 80 multiplied by 20. Correct? So how much are we getting? 4.5 grams. So what is the oleum labeling? Oleum labeling will be equal to 104.5 percentage. Correct? This is the percentage labeling we have to do. Okay. Now, same way, let's do for this one now. See, 1 gram of SO3, 1 gram of SO3 is present in how many grams of oleum? 6 grams of oleum. Correct. This is present in 6 grams of oleum. Then 100 grams of oleum will corresponds to how much amount of SO3? 100 grams of oleum corresponds to how much amount of SO3, everybody? Okay, so check out. So that is the weight of SO3, excess amount of SO3, which is equal to 100 by 6. Now do the same thing. What is the weight of H2O? Weight of H2O is equal to 18 by 80 into weight of SO3, which is 100 by 6. Okay. So this I'm getting it as 3.75 grams. So therefore, percentage labeling is equal to 103.75 percentage. Right, Samyak? Now Is there any amount that we can, label, or is there any restriction? See, how much maximum you can label the solution, beta? To what extent we can label the solution? Check it out. Suppose if I take oleum, in which everything is SO3 only, and I have not added any H2SO4 at all. Okay, I have not added any H2SO4 at all. Then, clear. Then what is the labeling of it? So you know that now the weight of H2SO4, original is 0, but weight of SO3 is 100 grams. So weight of H2O that is to be added is 18 by 80 into 100, correct? 18 by 80 into 100. Now this is coming as 22.5 grams. So which means maximum labeling of oleum, theoretically how much you can give is 122.5 percentage. So 130 percentage oleum means it is absurd. Is that clear, beta? So maximum only this much you can label. Okay, between 100 to 122.5. This is the boundary of the labeling. Okay. So if somebody sends you 130 percentage of labeling, हमें what will you do? आप वापस भेज दो उसको, बोले नहीं चाहिए, तुम्हारा कंसेंटमेंट नहीं चाहिए, वो डुप्लीकेट. Correct? So it should be somewhere in there. In fact, you should never go for something like this, isn't it? You should go something as simple as 109 percentage like this, correct? Because that is the best export you can make, because you are bringing a more stable solution. Got it? If you bring only SO3 means you'll have more gas, easy to leak. Got it? So these are the industrial standards that need to be maintained. Now, check the next question. A sample of oleum is labeled this way. If the density of oleum is given, find the molality and molarity of oleum. Right? Everybody check into it. So what are we getting? Weight of H2O is 6.75 grams. That is the extra weight that you have added. So X will be equal to 80 by 18 into weight of H2O. I'm writing this reverse way. This is the excess amount of SO3. So excess amount of SO3 will be equal to 6.75 into 80. 80 into 6.75 divided by 18, and this is coming out to be 30 grams. So this is excess of SO3 added to convert that into oleum. Okay. So now the weight of the oleum is how much? Weight of oleum, correct? If it is 100 grams, then weight of, sorry, for 100 grams, what is the density? Density given is 1.5 gram per ml. So what is the volume of the solution in that case? Volume of the solution will be 100 into 1.5. So which makes it 150 ml. Correct? 150 ml is the solution. So now what is the molarity? Molarity is equal to number of moles of H2SO4 that was originally added, that divided by volume of solution. Correct? So now notice how much is the weight of sorry, H weight of SO, number of moles of SO3, sorry, number of moles of SO3, which is the solute added to sulfuric acid, correct? So solvent weight also I'll write down. Weight of the solvent, which is equal to weight of H2SO4, that is 70 grams. So number of moles of SO3 will be equal to 30 divided by molar mass, 80. This will be the number of moles of SO3. And that divided by volume. Volume is given as 150 ml. So 150 into 100. Correct? So this will be equal to how much? 90 by 16. So 3 is 5.625 molar. This is the molarity.
Sir,
Yes, beta.
sir, volume 100 by 1.5 है कि 100 into 1.5?
Sorry, 100 by 1.5. मैंने उल्टा लिख दिया. So 100 by 1.5. So this 1.5 will come up. Okay. वही calculations के basis पे. 100 by 1.5 into 1000. Okay. Right. So let me check how much we are getting. So 30 into 1.5 into 10 divided by 80. So 5.625 molar. Now we got the molarity. How do we get molarity? If you recall the formula, percentage molarity is equal to, okay, molarity is equal to 1000 times of molarity by 1000 times of density minus molarity into molecular weight of solute. Okay, so just substitute that value. 1000 into 5.625 divided by 1000 times of density minus 5.625 into 8. After you work out, this is coming out to be 5.35 molar. Done, everybody? Please check.